We're going to talk about modularity and communities in this lecture. We're going to use the star graphs again to get us started and review what we said about it being a vulnerable graph. We're also going to revisit the 2R regular graphs and other generalized stars. We're going to talk about nested graphs and motifs. So in the last lecture, we talked about the star graph, and we noticed that the star graph is also a complete bipartite graph with one vertex in one of the partite set and all of the other vertices in the other partite set. Well, we can also think of the star graph as our 2R regular graph, where it's a K1 plus M copies of a K1. So it's about as simple as you can get, but it is the same structure that we looked at with the 2R regular, and it is a 2-1 regular graph. But looking at it with this structure allows us to more easily replace the central vertex of the star graph with another graph, because we could replace the K1 with a K2. We still have the same format, and we still have a 2R regular graph, but now we have created a graph that is more robust with respect to connectivity. So if we look at this KS plus MKPs again, we could ask, what would it take in general to disconnect this 2R regular graph? If we would have to remove, in fact, all of the vertices in the KS, since it's completely joined to the M copies of KP. But removing all the vertices of the KS, in other words, removing the KS, is the same as removing the central vertex of the star. We would then wind up with M disjoint graphs. We're going to continue to use the KS plus the MKP to study the community structures and also hierarchical graphs. We can say that this graph, our 2R regular graph, has M plus 1 communities, where each of the KPs on the periphery represent a community, or notice that they are completely joined to the KS, so they form a community of size S plus P. When we think of them forming a community of size S plus P, we notice then that these communities overlap. They overlap with the S vertices. Or we could also let the KS be a community in itself, and that's why I said M plus 1 communities. And methods of finding communities are similar to what we've talked about in finding clusters or dense subgraphs. Oftentimes, in finding communities or in constructing a graph that has communities, we construct what is known as a hierarchical graph. So if we look at the network below, then this is an example of a hierarchical graph. It also looks like our star graph, except that we're not using complete graphs, or our 2R regular graph, like we do in our 2R regular graph. The graphs on the periphery are what is known as a wheel, rather than a complete graph. And so is the graph in the central vertex. And then we have connections, but not a join. That is, not every vertex in a graph on the periphery is joined to every vertex in the central graph. So we have sort of the star graph structure, but we have fewer edges. Why would we want fewer edges? Well, one thing that we have talked about as far as the 2R regular graph is that they have the two defining properties, that they have a high clustering coefficient and they have a low average path length. But one thing we have not emphasized is the fact that these are fairly dense graphs with respect to the overall structure. Ideally, what we want is the high clustering coefficient, a low average path length, with relatively few edges. We want to be able to achieve that without the graph being too dense. This comes back to this idea again of combinatorial optimization. We have conflicting constraints and we want to find an optimal place where we can achieve the best given these conflicting or competing measures. So nested subgraphs is a way that we can perhaps remove some of the edges from our regular graph, and therefore the graph is more sparse, and yet it has the high clustering coefficient and the short average path length, and it remains the property that it is robust, meaning from the previous lecture that it can withstand attacks or changes in its structure without losing its defining properties. So what we want to do is, again, create a graph that is robust but more sparse than the examples that we have seen so far. So if we begin with our KS plus M copies of a KP and think of it as a generalized star, where the vertices in the star have been replaced with a complete graph, then how could we make it more sparse? The natural thing to do would be to say, well, let's take the complete graphs and replace them with a graph that is not complete, but still highly connected. So what should we replace those graphs with? Well, one thing that we could think of doing is replace each of the complete graphs in the periphery with another to our regular graph. That is, if we still have the graphs on the periphery being of order P, there are still P vertices, but we will identify R of them and make that our KR, and take the rest and make them KTs for some T, such that M times T plus R is our P. But now we have fewer edges if we create a KR plus M times KT than we had if we had a complete graph on P vertices. And then how could we join this graph to the KS and the KS plus MKPs? We could perhaps just join the complete graph KS to just the KR. So we're removing edges within each of the complete graphs on the periphery. We're removing edges connecting to the complete graphs on the periphery. This is a type of, another type of hierarchical graph. And this was the topic of Josh Brooks' thesis, which I believe is included in the folder on D2L. In studying these communities, we find repeated structures that we call motifs. Motifs are sometimes also called dense subgraphs. So what is the difference? Motifs typically refers to some type of functionality. So you have these identifiable small subgraphs that are associated with a particular function of the network. And so for a very small motif, there are 13 well-known motifs that use 3 vertices. And notice that these vertices or these motifs are directed graphs. Because if you don't have the direction, you certainly don't have 13 possibilities. But there are 13 motifs that deal with concepts from engineering principles, the feed-forward loop and the feedback loop, and these have been identified in things like gene regulatory networks. So this is a large area of study in the study of biological networks, and we'll return to the concept of motifs in Chapter 5. But again, a motif is similar to a cluster, but motifs are more often associated with a given function. So that is one distinguishing difference in biological networks with other networks in general, is there is an underlying assumption that the structure of the network is highly correlated to its function. If you have a large network, then you can classify it by looking at its structural motifs, its structural communities, and say that two networks are similar if they are built from the same set of motifs. Now, you can be talking about a large gene-gene or protein-protein interaction network, or even a gene-protein interaction network, or you may just be talking about a single protein. A single protein can still be considered a network if you consider every amino acid as a vertex. And then two vertices are connected if those amino acids are close in the three-dimensional structure of the protein. Then proteins, in that sense, are an interacting network of amino acids. So we saw that we can look at secondary RNA structure from a network or graph theoretic point of view. We can also do the same thing for protein structures. And there's quite a bit in the literature about classifying protein structures by studying the similarities of their motifs. So we've looked at star graphs and used those and realized that they are also 2R regular. In particular, they're 2-1 regular. We can generalize the 2R regular graphs by replacing the complete subgraphs that define them with other graphs, and thereby hopefully maintaining the high clustering coefficient and the short average path length, but coming up with a graph that is more sparse, because the naturally occurring networks that we find that are small world tend to be able to achieve those two properties with relatively few edges. In our next lecture, we're going to introduce graphlets. Graphlets are also going to be discussed in Chapter 5, so we're just going to introduce them here and then return to them later. But graphlets use both the ideas of generalized degrees and common motifs.